Okay, here goes. We're doing 5.3, solving trig equations. And when we solve these trig equations, our goal is to get the trig function on one side of the equal sign. We're going to isolate the trig function. So here we go with the first example. If I think about isolating cosine x, I know what my first step has to be. I'm going to get rid of that 1. I'm going to subtract the 1 from both sides. And then finally, to set the cosine x free, I'm going to divide both sides by -2. And I get cosine x equals 1/2. So we're looking for an angle that has a cosine equal to 1/2. And maybe what might be nice for us to do is to remind ourselves real quickly about the first quadrant, where we have pi over 3, and that's 1/2 root 3 over 2. And we've got pi over 4, which is root 2 over 2, root 2 over 2. And we've got pi over 6, running enough room here, which is root 3 over 2 and 1/2. Just remembering that first quadrant is going to be very helpful. So when we think about where what angle has a cosine of 1/2, we see that pi over 3 does. So we could say, yay, we're done. X equals pi over 3, but then we realize, wait a minute, there are other angles who have a cosine equal to 1/2. Just within the first 2 pi, just within the first 4 quadrants, without going around another revolution, we know that cosine is positive in the first and the fourth quadrant. So if we think about our bow tie, we know that down here at what, let's see, 5 pi over 3? 5 pi over 3 is also going to have a cosine of, so I'm going to write this here, x equals 5 pi over 3. You may wonder, why am I writing them separately? Because we know that there are even more angles that have a cosine equal to 1/2. When we go back to pi over 3, let's go back to pi over 3. When we're going back to pi over 3, and we know that if we take pi over 3 and add another full revolution, another 2 pi to it, then that would give us, what, 7 pi over 3, which also has a cosine of 1/2. So instead of writing 7 pi over 3 and then what, 13 pi over 3 and keep adding 2 pi to it, we're like, well, we can cover all those angles by saying pi over 3 plus 2 pi n, where n is an integer. N is an integer. We'll have this agreement from here on out about n, that n is an integer where, where n is greater than or equal to 0. Because if we have n equals 0, we have pi over 3, and then when n equals 1, that means that's 1 revolution around. That's pi over 3 plus 2 pi, which is that 7 pi over 3, and keep going around and around, right? Because all of those angles are going to have the cosine equal to 1/2. And then when we look at the answer 5 pi over 3, we're going to do the same thing with 5 pi over 3. We're going to, if we do an evolution of 2 pi all the way around, well, let's see, 5 pi over 3 plus 6 pi over 3, that would be 11 pi over 3. Well, cosine of 11 pi over 3 is also 1/2. And we can keep going round and around, but we know that we can capture all the answers by saying 2 pi n, where we already have the agreement that n is an integer greater than or equal to 0. Okay? And this, my dear pre-calc students, is our answer for what angle has cosine equal to 1/2. Okay, let's look at the next one. We see that we want to isolate the trig function of sine, but we have it on both sides. So why don't we go ahead and add sine, or we could subtract sine. Either way, why don't we subtract sine x from the left side, which gives us what? Sine x minus another sine x is minus 2 sine x's, and then we're going to divide both sides by 2, which gives me a negative 1/2. And so let's think real quickly about where sine, what angle has a sine equal to negative 1/2. When I think about the 4 quadrants, I think about sine being negative in what, the third? And and the fourth quadrant, all right? And so we know that it's going to be an angle in the third and the fourth, and I'm going to use my reference angle in the first quadrant to remind me that where sine is equal to 1/2, that is what, pi over 6. That's where sine is equal to 1/2. But where is sine equal to negative 1/2? Well, let's see, this would be what, 11 pi over 6? And this would be 7 pi over 6. Okay, so once again, we have two angles. We've got the 7 pi over 6, so x is equal to 7 pi over 6. And x is also equal to 11 pi over 6. We're going to go back and do the same thing, talking about evolutions or revolutions. If we take the 7 pi over 6 and we add another 2 pi to it, we'll get what? 19 pi over 6. That would also have a sign that's equal to negative 1/2. And so instead of listing all the angles that we're going to get by adding 2 pi and 2 pi and 2 pi, we just put plus 2 pi n, where we already have that agreement that n is an integer greater than or equal to 0. We'll do the same thing for 11 pi over 6. We're going to add 2 pi n. So there's really an infinite amount of angles that have the sign equal to negative 1/2, and we just named them all in a very concise way. Pretty cool. Okay, so here we want to get tan alone, so we're going to go ahead and add tan to both, we're going to add 3 to both sides. And we're going to go ahead and take the square root of both sides. If we take the square root of both sides, we get tan x is equal to plus or minus root 3, right? If I take the square root of both sides, I have to put a plus or minus in front of my number, which gives me two problems, right? Either tan, we want to find all the angles whose tan is equal to a positive root 3, and we want to find the other angles whose tan is equal to a negative root 3. And so we need to figure out, first of all, where is sine over cosine equal to root 3? And then we'll just talk about the negatives because that's really just the quadrant. So I think about all my different options, right? We could do, I think about pi over 6, where we'll have the root 3 over 2 and the 1/2. And since tan is sine over cosine, that would give me not quite my answer, so that's not going to be it. I think about pi over 4, that's root 2 over 2 over root 2 over 2. Nope. So let's go ahead and look at pi over 3. Why not? With pi over 3, we know that cosine is 1/2, and sine is root 3 over 2. So if we went ahead and put sine, so this is pi over 3, if we put sine over cosine for pi over 3, we get, our 2's cancel out, and we get a root 3. So we know that we're dealing with one of the bow ties of the angle pi over 3. So I want you to stop for just a second and see what I did, because I'm using chapter 4 stuff right now, right? Where we know that tan is sine over cosine, and we know that we've got 3 reference angles that we reference a lot in the first quadrant. And pi over 3 is the only one, because pi over 3 is 1/2 for cosine and root 3 over 2 for sine. That's the only one that's going to give me a tan of root 3. All right, so for the positive root 3, we can say that's one of my answers. I've got pi over 3. Where else is tan positive? Well, let's think about it. Tan is sine over cosine, so it's going to be positive in the first quadrant, where sine and cosine are both positive. It's also going to be positive in the fourth quadrant. See if I can draw this a little bit better. Okay, it's going to be positive in the fourth quadrant, where both sine and cosine are negative. So in the fourth quadrant, what do we have? We've got 3 pi over 3 plus another pi over 3, so that's 4 pi over 3. Okay, so, but, ooh, look, this is really special, especially it would be extra special if I actually drew it even a little bit more accurately. Because we notice, hey, pi over 3 and 4 pi over 3, that's just pi over 3 plus pi, which is going to give me a 4 pi over 3. And then to get back around, if I keep doing my revolutions, right, I have another pi and another pi. This is a really cool answer because we realize that we can just add a pi n because our answers, our two answers, our original angles that we want are pi away from each other. We didn't have that pattern before in the other answers, so we had to do both of them separately and add a 2 pi n. But when we have something that looks like this, we just add pi n, which is pretty cool. All right, let's talk about what happens when tan is equal to negative root 3. Well, we still know it's going to be part of the pi over 3 bow tie, but it's going to be negative. So where's tan negative? Tan is negative right here at what, 2 pi over 3? And it's negative right here at 5 pi over 3. So once again, we have two angle answers, and our answers are separated by pi. So if I wrote down my first answer, which is 2 pi over 3, I don't have to write plus 2 pi n, because what I've got is, I've got 2 pi over 3 plus pi, which gives me a 5 pi over 3, plus pi, plus pi, plus pi. So that's what we're going to add to our answer, plus pi n. So this is quite an answer. Both of these will give us the infinite amount of angles that will make this equation work. All right, let me double check my answers. Always good to do that. All right, so let's look at the next example. Whoa, we got a lot going on here, right? And so what we don't want to do is divide by both sides by cosecant x, because we don't know whether cosecant x has a value of 0, so we don't want to be doing that. So what we're going to do is get all the trig functions on the same side. We're going to subtract that cosecant x from both sides. Oh, I always forget that c. Okay. Checking the time real quick. Okay. And we see that we've got two terms, right? We have secant x, cosecant x, minus another term, cosecant x. And we see that both those terms have something in common. They both have the cosecant x in common. So I'm going to go ahead and factor that out. Remember, factoring is basically just dividing both terms by what you're taking out. So we're dividing the first term by cosecant x, which leaves me with secant x. And we're dividing the second term by cosecant x, which gives me 1. And you're like, okay, so my C turned into an, okay. I'm fighting a virus, or I shouldn't say I'm fighting it. I mean, I guess my immune system's fighting it. But I have a virus right now, which makes me want to double check my work. Let's see. All right, so then you're like, well, Miss Overby, that still doesn't look good. So we're looking at it. The nice thing about this, though, is we have something times something equals 0. So we can do our 0 multiplicative property, or multiplicative property is 0, which says either cosecant x equals 0 and or secant x minus 1 equals 0. So we're going to go ahead and solve now two smaller equations, cosecant x equals 0 and secant x equals 1. So let's talk about cosecant x equals 0. All right, let's look at cosecant. First of all, we know that cosecant is the same thing as 1 over sine, right? So really we're saying, well, this really helped to write it down because, right, we're saying, hey, when does 1 over sine x equal 0? I'm hoping that you're saying right now out loud or in your head, never, right? 1 over nothing is going to give me 0. And so this is impossible right here. We're not going to get an answer from this part of our equation. For a fraction to equal 0, the numerator has to be 0, so that's not going to happen. And then, of course, the sine x can't be 0 on the bottom. But the main reason why is we have this 1. We can't make a fraction with a 1 on the top ever be equal to 0. So good, farewell, good riddance. So let's look at secant x equals 1, and let's remind ourselves, what is secant x mean? It means 1 over cosine x. So when does 1 over cosine x equal 1? So let's go ahead and look at our quadrants, and let's think about where cosine is equal to 1. Well, it's equal to 1 right here, right, at 0, 2 pi. Is it equal to 1 anywhere else? Nope, 0, -1, 0. So this is the only place right there. So we're going to stop and say, well, x is equal to 0 plus 2 pi n. I guess we don't really need that 0, do we? Because we've already made the agreement that n is equal to an integer that's greater than or equal to 0. So we could rewrite this so it made more sense as 2 pi n. That's when n is equal to 0, it will give us our answer. Okay, once again, I want to double check. Yes, even with the virus, I got that right. All right, let's look at the next. Solve the following equation on the intervals 0 to 2 pi. Okay, I know what you're thinking. Oh no, intervals. Because we really haven't been a fan of intervals. But really, intervals are our best friends when it comes to solving trig equations. And why is that? Because we're limited. We now no longer have to do the plus 2 pi n or the plus pi n. And I'll show you what I mean when we solve this. So here we go. I'm looking at this and I'm like, ooh, it looks like, it reminds me of a quadratic, right? 2x squared plus x minus 1. And if I were to factor it, let's see if I can do this. If I were to factor it, I'm going to have a 1 here and a -1 here, right? I get my 2x squared. If I FOIL, and my plus 2x minus x minus 1. There we go. So this gives me my hint about what to do with this. So instead of factoring and having it say 2x minus 1, it's going to say 2 cosine x minus 1. And the second one, instead of x plus 1, I'm writing cosine x plus 1. And if you wanted to, if you didn't trust me or this method, you could go ahead and FOIL for yourself, right? You get 2 cosine squared x, and then you get the plus 2 cosine x and minus cosine x minus 1. There we go. All right, which is beautiful because when we factor, it gives me something times something equals 0. So I know either 2 cosine x minus 1 equals 0, or cosine x plus 1 equals 0. Here we go. We're going to isolate cosine x here. We're going to go ahead and add 1. We're going to divide by 2. And we get cosine x equals 1/2. So let's just stop and answer that real quickly. If we think about where cosine is equal to 1/2. Now remember, we're on an interval where 0 is included because there's the brackets. Goes from 0 all the way up to, but not including, 2 pi. So let's see. I know that cosine of x is equal to 1/2 when x is equal to pi over 3. Where else is cosine positive? Cosine's positive in the 4th quadrant. So I know that that's going to be 5 pi over 3, right? And that's it, because I can't do all my revolutions. I'm stopped. They only want me to list the angles that are equal to, greater than or equal to 0, and less than 2 pi. So that's the cool thing, is that there they are. My answers are pi over 3 and 5 pi over 3. Then let's look at this part of the equation. If I subtract 1 from both sides, I get, where's cosine equal to -1? And when I look at my unit circle, or just my quadrants, I think, okay, cosine is equal to -1 right here at pi, right? Is it equal to -1 anywhere else? Well, sure, if I do the revolutions, it could be at 3 pi and 5 pi, but we're not doing that because we're in a parameter of 0 to 2 pi. So x is equal to pi. So we're going to put those together. Our answer is x equals pi over 3, pi, I'm putting them in numerical order, right, and 5 pi over 3. So there we go. And I will double check just to make sure. Yep, looks good. All right, we have 2 more to go. Here we go. Okay, so this looks lovely, but very similar to what we just did, right? So we're going to first change this to a quadratic, so it helps us to understand what to do in our next step. When I think about factoring this, I think about putting two terms that multiply to equal 2x squared. I'm going to have to mess around with that 3 because I have to end up with a 3 from my middle term. Ooh, how am I going to do this? Uh-oh. Okay, let me look at my notes. Okay, I know why I made the mistake. And you know, I got to pause. I've got a phone call coming in. I will be right back. Okay, and I'm back. So yeah, this whole virus thing making me feel out of it and tired. I was not observant, but hopefully you guys were observant, and you're probably telling me, no, Miss Overby, we're not ready to do the quadratic formula, or not quadratic formula, but factoring, and we're not because look, this is a sine and this is a cosine. We've got to have the same trig function. So we're going to remind ourselves about something with cosine squared x. We know that cosine squared x plus sine squared x equals 1. And we're like, oh, this is awesome. If we go ahead and subtract sine squared x from both sides, we could use substitution, right? Because as long as we have two different trig functions in the same equation, we're never going to get to solve for it. We only can have one trig function in the equation. So instead of writing cosine squared x, I'm going to take this 1 minus sine squared x and flop it in where I see cosine squared x, because we're allowed to do that. We are allowed to use substitution. So we'll go ahead and plug in 1 minus sine squared x, and we'll rewrite the rest of the equation, and we'll distribute. And we'll combine like terms. Let's see. We're going to have negative 2 sine squared x plus 3 sine x. And then we have 2 minus 3, which is minus 1. And then who wants to factor with a negative 2 as your leading coefficient? I don't. So what I'm going to do is I'm going to multiply through by negative 1. So I'll multiply every term by a negative 1. I'm allowed to do this. It is legal. The equation looks different, but it's really the same equation since we did the same thing to every term. Now I can take this and rewrite it as 2x squared minus 3x plus 1. And we've used this strategy many times before in this class. And that is to take something that looks like a quadratic and change it into a quadratic so it reminds us what we can do as far as factoring, and then apply what we learned here back to the original problem. All right, so 2x times x gives me my 2x squared. I see a plus 1 and I see a negative 3. That means I'm going to have a negative 1 and a negative 1, right? Because if I do FOIL, my first is right, my second is negative 2x, my third is negative 1x, so that gives me negative 2x minus 1x is negative 3x, and my last one is a positive 1. So now, instead of writing the 2x minus 1, I'm going to write 2 sine x minus 1, and then I'm going to write sine x minus 1 equals 0. And I now have two factors. I can set them both equal to 0. Oops, I'm jumping ahead. I'm going to set them both equal to 0. And I'm going to solve. And I'm hoping that I have a parameter, that I'm in an interval. Yay! Because it's so much easier. Because it's basically saying, well, it is saying, what angle has a sine of 1/2? And we know that's what, pi over 6 has a sine of 1/2. What else is sine positive in the second quadrant? And that is 5 pi over 6. So those are my answers here, pi over 6 and 5 pi over 6. And then over here, where is sine equal to 1? Well, sine is equal to 1 right here, right? This is 0, 1, and that is at pi over 2. Sine is not equal to 1 anywhere else in the first from 0 to 2 pi. So let's just go ahead and write them all together. Our answer involves all of them. We've got pi over 6, we've got pi over 2, and we have 5 pi over 6. Does it matter which order we write them? No, I'm just writing them from least to greatest. All right, and we've got our last one, and then we're done. Okay, so once again, we have this problem where we have one equation, but we have two different trig functions, and that's not going to work. We can't solve an equation unless we have one trig function. So I'm like, well, and I can't use secant because it's not squared, and I can't change them to sine and cosine. That's not going to help. And so when all else fails, what do we do to solve equations, no matter what kind of equations they are? We square both sides. So let's do that here and see if we can make something happen. Now we have to remember, squaring both sides of an equation to solve it is like the last-ditch effort, and we have to be careful because we could end up with a solution that's not really a solution. All right, so here we go. Yes, an extraneous solution. I can just hear you say it. All right, so let's square this. We'll have what? Square the first plus twice the product of the two, and square the last equals tan squared x. And I'm like, you know what? Tan squared x, I got all these secants. Let's go ahead and do some work on that tan squared x. I know that we secant tan, right? Secant squared x equals 1 plus tan squared x. If I wanted to isolate tan squared x, I'd subtract 1 from both sides. So since this equation tells me tan squared x is the same thing as secant squared x minus 1, I am going to use substitution and plug that in. So I'll rewrite this side, keep that the same, and then I'm going to use substitution. Instead of writing tan squared x, I'm going to write secant squared x minus 1. And now I'm like, great, my equation, if it can be solved, it at least has a chance to be solved because I have all secants. And so here we go. Here we go. We're going to, let's see, let's subtract the secant squared x from both sides. Oh, it goes away, right? Let's add the 1 to both sides. So we get 2 secant x plus 2 equals 0. And thank goodness we can factor out the 2. Factoring is awesome. So we divided both terms by 2. And then we get two funny things. We get, well, one funny thing. 2 equals 0. Not, 2 can never equal 0, or secant x plus 1 equals 0. So let's keep going. We subtract 1 from those sides, and we have to remind ourselves that secant is 1 over cosine x. So we were really looking for where is cosine x equal to negative 1. And so I think about cosine, and I don't match this up with x. It's right here, right? This point is negative 1, 0. This point is pi. So what angle has the secant equal to negative 1? Pi. Okay, we need to double check that we don't have an extraneous solution. So let's go back to the original equation and make sure that works. Secant of pi, well, that's negative 1. So negative 1 plus 1 is 0. And then tan of pi, well, that's sine over cosine, which is 0 over 1. 0 equals 0. That works. That's a real solution. All right, it was fun. I happen to love these. I hope you're enjoying this too. Have fun with your homework, and I will see you in class.